Let's begin with a simple question. If I place you in the middle of the Sahara Desert with one vehicle, limited fuel, and just enough supplies to survive for a short time, could you return home safely? Maybe, but only if you planned the return before you left. Now stretch that desert to a scale so large that Earth becomes a small dot in the sky. Remove the air, remove liquid water, lower the gravity. Add radiation that slowly damages your cells. Make the temperature swing between deep freeze and mild warmth depending on the time of day. That is Mars. When people talk about going to Mars, they usually imagine the dramatic launch from Earth. Fire, thunder, smoke, acceleration. The rocket rises, escapes Earth's gravity, and months later touches down on the red planet. It feels like a one-way adventure. But physics does not see drama. Physics sees energy budgets and momentum exchanges. The real question is not, can we land on Mars? We already know we can land machines there. The deeper question is this: once humans are standing on Mars, can they leave again and return safely to Earth? Returning is not simply reversing the trip. You cannot just point the spacecraft toward Earth and press a button. Earth is not stationary. Mars is not stationary. Both planets are moving around the sun at tens of kilometers per second. So returning is more like trying to jump from one moving train onto another moving train, except both trains are curving around a star. To leave Mars, you must first climb out of its gravity well. Even though Mars has weaker gravity than Earth, it still holds you down. Gravity is not a force you can ignore just because it is smaller. To escape Mars, you must reach about 5 kilometers per second. That means your spacecraft must accelerate to that speed relative to the planet. And acceleration requires fuel. Fuel requires mass. And mass resists acceleration. Here is a simple thought experiment. Imagine you are at the bottom of a deep pit. To get out, you must throw bricks downward so that you move upward. Each brick you throw gives you a push. Rockets work the same way. They throw mass in one direction to move in the other. But if you want to climb higher, you must carry more bricks. And carrying more bricks makes you heavier, which means you need even more bricks. This is the heart of the rocket equation. So when we say, returning from Mars, we are really asking whether we can manage this energy and mass problem under extreme conditions, with no rescue team nearby, and no margin for large mistakes. That is the true beginning of the problem. It is not about bravery. It is about whether the laws of motion, gravity, chemistry, and human biology can be coordinated carefully enough to allow a fragile biological organism to leave one planet and safely reach another. To understand the return from Mars, we have to face the central constraint of space travel energy, not ambition, not funding, energy. In physics, moving from one place to another, especially between planets, is a matter of changing velocity. And changing velocity in space is expensive. Mars may have weaker gravity than Earth, but it is not negligible. If you stand on its surface and want to leave permanently, you must reach what we call escape velocity, about 5 kilometers per second. That number may not feel large, but think about it this way: a rifle bullet travels roughly 1 kilometer per second. To escape Mars, your entire spacecraft must move 5 times faster than a bullet. And here is the difficulty. Rockets do not push against the ground. They work by conservation of momentum. They throw mass backward at high speed, and in reaction, the rocket moves forward. The faster you want to go, the more mass you must eject. The more mass you carry as propellant, the heavier the rocket becomes. And the heavier it becomes, the more propellant you need. This circular trap is described mathematically by the rocket equation, and it is unforgiving. Imagine you are trying to cross a frozen lake by throwing stones behind you to slide forward. If you want to reach the far side, you must carry all the stones at the start. But carrying more stones makes you heavier, so you must throw more of them to move the same distance. At some point, the plan becomes absurd. You cannot carry an infinite number of stones. This is why bringing all the return fuel from Earth is inefficient. Every kilogram launched from Earth must first escape Earth's gravity, which requires enormous energy. Then it must be transported across interplanetary space, only to sit unused on Mars until the return trip. You end up paying an energy penalty twice, once to lift it from Earth, and again to lift it from Mars. Physics suggests a more elegant solution. If Mars already has the raw ingredients for fuel, perhaps we should use them. The Martian atmosphere is mostly carbon dioxide. Beneath the surface, there is water ice. With electricity and the right chemical processes, carbon dioxide and water can be converted into methane and oxygen. Methane can serve as rocket fuel. Oxygen acts as the oxidizer. Together, they form a propellant combination that is efficient and relatively well understood. This approach changes the mass problem dramatically. Instead of launching a fully fueled return rocket from Earth, we launch a smaller vehicle and a fuel production system. The system arrives first and begins manufacturing propellant using local resources. Months later, astronauts land knowing that their ascent vehicle is already filled. This idea is not fantasy. It is based on known chemistry and tested reactions. The challenge is reliability. The equipment must function autonomously in a cold, dusty, low-pressure environment for months before humans even arrive. If it fails, the crew has no way home. So the energy problem is solvable in principle. But solving it requires careful accounting of mass, chemistry, and time. The laws of physics allow the return. They simply demand precision. If we solve the energy problem by producing fuel on Mars, we move from pure physics into engineering reality. And engineering reality is where optimism meets friction, dust, corrosion, and time. The idea sounds simple when stated in one sentence: use Martian resources to manufacture rocket propellant. Mars has a thin atmosphere made mostly of carbon dioxide. It has water ice locked in the soil and at the poles. Combine carbon dioxide with hydrogen derived from water, and through a chemical process known as the Sabatier reaction, you can produce methane and oxygen. Methane burns cleanly and efficiently. Oxygen supports combustion. Together, they form a practical rocket fuel. In the laboratory, this works beautifully. In controlled environments on Earth, we can run this reaction continuously. We can split water into hydrogen and oxygen using electricity. We can liquefy gases and store them in tanks. None of this violates physics. None of it is speculative chemistry. But Mars is not a laboratory. Imagine you leave a small automated fuel factory alone in Antarctica for a year. It must operate through freezing temperatures, dust accumulation, mechanical wear, and power fluctuations. Now remove the maintenance crew. Remove spare parts. Add communication delays of up to 20 minutes each way. That begins to resemble the Martian challenge. The machinery must extract water from soil or ice deposits. That requires digging, heating, filtering. The water must then be purified. Electrolysis units must split it into hydrogen and oxygen. Compressors must capture carbon dioxide from the thin atmosphere. Reactors must maintain precise temperatures and pressures for the chemical reaction to proceed efficiently. Then the methane and oxygen must be cooled into liquid form and stored cryogenically, meaning at extremely low temperatures, for months without excessive loss. Each of these steps is individually manageable. Together they form a chain, and a chain is only as strong as its weakest link. Dust is one of the least glamorous but most serious concerns. Martian dust is extremely fine and electrostatically clingy. It can infiltrate seals, coat solar panels, degrade moving parts. Over time, dust reduces efficiency and increases mechanical strain. Unlike on Earth, there is no rain to wash it away. Power is another constraint. Solar panels receive less sunlight on Mars than on Earth, and dust storms can reduce output dramatically. Nuclear power sources provide stability, but introduce complexity and mass considerations. The fuel production system must operate steadily for months, possibly over a year, before humans depend on its output. There is also the issue of storage. Liquid oxygen and methane must remain cold. Thermal control systems must prevent boil-off. If too much propellant evaporates into space, the return vehicle may not have enough thrust to escape Mars. So when we say we will make fuel on Mars, we are compressing an intricate network of systems into a short phrase. The chemistry is known. The thermodynamics are known. What remains uncertain is long-term reliability under alien conditions. This is not a barrier imposed by nature. It is a demand for precision. Mars does not forbid us from making fuel. It simply refuses to forgive sloppy engineering. Suppose the fuel has been manufactured successfully. The tanks are full. The ascent vehicle stands on the Martian surface, waiting. The next step is no longer chemistry. It is orbital mechanics. Leaving Mars is not enough. You must leave Mars at the right time, in the right direction, at the right speed. Imagine you are standing in an open field, trying to throw a ball into a moving truck that is circling you at high speed. If you throw too early, the truck won't be there. Too late, and it has already passed. Too slow, and the ball falls short. Too fast, and it overshoots. Returning to Earth from Mars is like that. except the truck is Earth, and both planets are moving around the sun at tens of kilometers per second. Mars orbits the sun more slowly than Earth because it is farther away. Earth completes one orbit in about 365 days. Mars takes about 6 at 87 days. That means the alignment between the two planets constantly changes. There are specific windows, roughly every 26 months, when the geometry allows an energy, efficient transfer from Mars back to Earth. If astronauts miss that window, they cannot simply try again next week. They must wait more than 2 years for the next favorable alignment. That timing constraint shapes the entire mission design. When the return window opens, the spacecraft must launch into Mars orbit and then fire its engines again to enter what is called a transfer orbit around the sun. This orbit is not a straight line. In space, straight lines rarely get you where you want to go. Instead, you follow an ellipse that gradually intersects Earth's orbit at the exact time Earth arrives at that point. This is known as a Hohmann transfer orbit. It is one of the most energy-efficient ways to move between two circular orbits. The mathematics is well understood. We have used it many times with robotic missions. The equations describing it were worked out long before humans ever reached space. So in terms of pure celestial mechanics, there is no mystery. Gravity behaves predictably. The sun pulls on Mars and Earth in calculable ways. If the spacecraft's velocity change is accurate within small margins, it will intersect Earth's orbit months later. But small errors accumulate. If the departure burn is slightly off in magnitude or directions, the spacecraft may miss Earth by thousands of kilometers. In interplanetary space, tiny angular deviations grow over millions of kilometers into large positional errors. That is why navigation systems must constantly track position and perform small correction burns during the journey home. Then comes Earth re-entry. Arriving at Earth is not the same as landing safely. The spacecraft will approach at high velocity, typically around 11 kilometers per second relative to Earth. That is fast enough to generate enormous heating as it compresses the atmosphere in front of it. The heat shield must survive temperatures hotter than molten lava. If the angle of entry is too steep, the spacecraft burns up. Too shallow, and it skips off the atmosphere back into space. The path home is not dramatic in appearance. It is a quiet arc shaped by gravity and numbers, but it demands precision across millions of kilometers. The comforting fact is this: gravity is consistent. The unsettling fact is this: it is consistent whether or not you calculate correctly. Even if every calculation is perfect, every engine burned precise, and every tank filled exactly as planned, there remains a system far more delicate than any spacecraft component, the human body. A machine can tolerate cold storage, radiation exposure within design limits, and long periods of inactivity. A human organism cannot be turned off and stored. It must function continuously, adaptively, for the entire duration of the mission, likely 2 to 3 years from departure to return. Start with microgravity. During the months traveling to Mars and the months returning, astronauts live in near weightlessness. On Earth, your muscles and bones are constantly under load. Gravity pulls you downward, your skeleton pushes back. This continuous stress maintains bone density and muscle mass. Remove gravity, and the body begins to economize. Muscles shrink because they are no longer required to support weight. Bones lose calcium because structural reinforcement is metabolically expensive. Astronauts on the International Space Station exercise about 2 hours per day to slow this degeneration. Even so, bone density decreases measurably over months. A Mars mission would involve far longer exposure. Upon return to Earth's gravity, weakened bones are more susceptible to fracture. Muscles may struggle to support normal movement. Rehabilitation would be required, and we do not yet have multi-year data on deep space exposure. Then there is radiation. Earth is protected by a magnetic field and a thick atmosphere. Together, they shield us from a large fraction of cosmic radiation. In deep space, that protection disappears. High-energy particles from the sun and from distant supernovae pass through spacecraft walls and human tissue. Some of these particles can damage DNA directly. Others create secondary radiation cascades inside the body. We understand radiation in terms of probability. A certain dose increases cancer risk by a measurable percentage. But the long-term neurological effects of chronic exposure to galactic cosmic rays are not fully understood. Animal studies suggest potential impacts on cognition. Whether similar effects would appear in humans over a Mars duration mission remains uncertain. Isolation adds another layer. Humans are social organisms shaped by millions of years of evolution in dynamic, open environments. A Mars crew would live in confined spaces with limited sensory variation, delayed communication with Earth, and no possibility of emergency evacuation. Communication delays of up to 20 minutes each way eliminate real-time conversation. Every message becomes more like sending a letter than making a phone call. Psychological stress is not dramatic in appearance. It accumulates quietly. Small conflicts can intensify when there is no physical separation. Monotony can dull cognitive sharpness. Anxiety may increase when individuals know that help is millions of kilometers away. Life support systems must also function flawlessly. Air must be recycled. Carbon dioxide must be removed. Water must be purified and reused. A failure in environmental control is not inconvenient, it is fatal. The human body is resilient within Earth's conditions. In deep space, it operates near the edge of its evolutionary design. Returning safely from Mars is not only about transporting mass across distance. It is about preserving the integrity of a living system through an environment it was never naturally built to endure.